fundamental theorem of algebra, Descartes' rule of signs, and also the rational zero theorem. Today we're pretty much going to be looking at determining the possible number and type. We won't actually be finding the actual zeros, but narrowing down from an infinite amount of possibilities to a discrete amount. So, our fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is larger than 0, so I'm done with any polynomial, linear or greater, then f has at least how many zeros? 1 0. 1 0 in the complex number system. Why the complex number system? What if we have here I have a polynomial of degree 2. Has at least 1 0 according to what we just said. What's the maximum number of zeros it can have? 2, right? Anything larger, it can't have 3. This is the second degree polynomial. So, how do I find my zeros? Sorry? Square root of both sides. This equals plus or minus I. There are the two zeros. Negative I and positive I. No real zeros here at all. This is where, again, the fundamental theorem says it has at least 1 0 in the complex number system. It doesn't have to be in the real numbers. Real numbers, complex numbers though are made up of what? What type of numbers?
Real numbers.
Real numbers and imaginary numbers. So when we say complex, it doesn't mean it's going to have an imaginary part to it necessarily. It could just be a real number. So here, we also have the linear factorization theorem. If f of x is a polynomial of degree n, where n is greater than 0, so linear or above, then f has precisely n linear factors. Whatever degree I have, that's how many factors I have. Fourth degree polynomial, I'll have 4 linear factors. When I break it all down to x minus something, right? Whether it's a complex number or real number, I'll always be able to have exactly n of them. Therefore, a polynomial of degree n has exactly n complex zeros. Again, as I said before, right, complex doesn't necessarily mean it's imaginary. It can also just be a real number. So one of the tools that help us find these zeros or to fine-tune it is Descartes' rule of signs. It's useful to determine the number of real zeros in a polynomial. One thing that it doesn't do, it's not going to find those roots, so we don't. It's not going to find those roots, it's not going to find those zeros. What it is going to do is tell us how many possible zeros are there. And the whole thing behind Descartes' rule of signs is all we're doing is counting up the number of sign changes. That's all there is to it, folks. From this, just counting up going from positive to negative, negative to positive, that's 2. That helps us determine, hey, there's 2 real zeros, 2 positive, 2 negative.
Can you say real Sorry, I didn't say
Minus 5 for you. So, with this, Descartes' rule of signs, the number of positive real zeros is either equal to the number of sign variations of f of x. Again, going from positive, negative, negative to positive. Or less than that number by an even integer. So, for instance, we have f of x equals negative 2x cubed plus 5x squared minus x plus 8. How many sign changes do I have? I'm starting off with what? Negative. From negative to positive, there's 1. There's 2. So we have sign changes 3 times. So this tells me the total number of possible real zeros, positive real zeros, is 3, or an even number less. What's an even number? So 3 minus 2. So this tells me I'm either going to have 3 or 1 positive real zeros for this particular polynomial. There are no other choices, 3 or 1. So it definitely helps taking an infinite amount of choices. Now I know it's either 3 or 1. Yes?
So if it went instead like 5x squared plus x plus 8, that wouldn't count as a sign change?
Nope, not at all.
2.
Correct. Negatives. To determine the number of negative real zeros, it's either equal to the number of, again, sign variations, but this time not of f of x, of f of negative x. We evaluate our function, replacing x with negative x, and then seeing what's going on with the signs. So it's either going to be the number of sign variations or less than that number by an even. The only difference between the positive and the negative is we're evaluating f of negative x for the negatives and f of x for the positive. So again, this is my f of x, negative 2x cubed plus 5x squared minus x plus 8, but that's not what we're looking at. For the negative real zeros, we're going to look at the negative x. So again, all we're doing is evaluating my function at negative x, replacing x with negative x, and then seeing what signs we have. So what do we wind up with here? Remember, if it has an even exponent, what happens to the negative? It goes away. Not exponent, I'm going to change that sign. So here, how many sign changes do we have? 0. Everybody here is positive. Right? So there are no changes in sign. So this tells me I have negative real zeros. We don't take less than that, right? Because then we're talking about a negative amount. So here, as small as we can goes to 0. I have no negative real zeros. This helps out, in particular, if you know, hey, I have 20 different zeros to choose from. I don't know which ones, half positive, half negative. If you come up with something like this, you know, I don't even have to look at those negative choices. I'm just going to look at the positives. Right? So, why do we keep saying always decrease the possibility by an even integer, or in this case by 2? We keep on, the 3 minus 2 is 1, so 3 and 1. Well, perhaps if we have 2, keep on decreasing it by 2. Well, the whole thing is, the further we work on down with the polynomials, eventually we get down to a quadratic. Starting off with the 3rd degree, I know a factor, I now have a 2nd degree quadratic. When we solve that quadratic, Sometimes you may actually have an imaginary root, an imaginary zero, which always come in pairs. Okay? Because they come in pairs, this is why we always subtract 2 using the start rule of signs. I had 7 sign changes. I'm going to decrease by 2, decrease by 2, decrease by 2. Because again, it always can occur that I have a complex number, but it always appears in our conjugate pairs. So here we have f of x equals a negative 4x to the 7th plus x cubed minus x squared plus 2. We're going to find the possible positive and negative real zeros. What is the degree of this polynomial? How many zeros can I have? 7. How many turning points? Review, right? Review is always good. So how many positive real zeros can I have here? John? What do we do? Okay, so I'm starting off with what? So that's 1. So how many positive real zeros can I have? Absolutely. Since there are 3 sign changes, it tells me it's either going to be 3 or an even number less, 2. So 3 minus 2. It's either going to be 3 or 1. Positive real zeros. For my negative, yes.
So this 5, would it be 3 or 1? So 5, 3, and
Absolutely. With 7, 7, 5, 3, or 1, 6, 6, 3, or 6, 4, 2,
so you
0. All goes down to 0 or to 1. Correct. So how do we find those negative real zeros? And what is f of negative x? Remember, if it's an odd exponent, I'm going to do what? Change the sign. Change the sign, right? Because the negative stays with it. If it's an even, keep the sign what it is. So here, what do we get then? 4x to the 7, sign changes. Minus x cubed. Minus x squared, sign doesn't change. So, what do we have here, Ellie, as far as my sign changes? Well, it starts off with a positive or negative.
Oh, it starts off with it.
So it went from positive to negative.
That's 1.
And then what?
And that one doesn't count. So then 2.
Absolutely. So from positive to negative, and then that negative to positive. So we do have 2 sign changes. So we have either 2, absolutely, 2 or 0 negative real zeros. I mean, this is helpful also. I mean, again, definitely limits what we're looking for. But if I already knew that I had 1 negative real zero, I already knew that x equals negative 1 was one of my choices. How many negative real zeros do I have? They let you know in the beginning. They said x equals negative 1 is a 0, is a solution. 2. Absolutely. My only two choices is I'm either going to have 2 negative real zeros or 0 negative real zeros. Well, if they already given me one of them, I know that there is a total of 2, so I know there's one more. This is where this comes in helpful. Here we want to find the same thing. F of x equals 2x to the 6 minus 3x squared minus x plus 1. How many turning points? 5 turning points. What are my positive real roots or real zeros? How many? I'm sorry? Two or 0. So as we have our positive to negative, and then that negative to positive, so 2 again, or an even number less. Once again, to evaluate, find out those negative real zeros. What do I get with f of negative x? Absolutely. 2x is 6 minus 3x squared plus x plus 1. Telling us what? Sorry? Or? Exactly. We have 2 sign changes from the positive to the negative, and then negative to positive. So 2 number less. That's all there is with these cards rule of signs. Questions on it? Doesn't get any more complicated than that. But that's not the only tool that we're going to use. We also want to talk about the rational zero theorem. We have our polynomial f of x equals a sub n, x to the n, always down to the constant term a naught. With our integer coefficients, every rational zero is going to have the form of p over q. What is a rational number?
A number that has a stopping point doesn't go on forever.
So are you telling me that 1/3 is not a rational number?
Yes.
It is a rational number.
1/3 is what? 1/3 is the decimal. That is.
Rational number, if you express it as a decimal, a non-repeating. It does not repeat. So something like 1/3, which you can express as 0.33 repeating, is a perfectly fine rational number. Any rational number you can express as an integer over an integer, such as 1/3. Unlike the square root of 2, which is what? 1.414213562237, or even our pi. Irrational numbers. So here, when we're talking about rational numbers, we can find out every possible rational zero by the rational zero theorem. We take our p, which are just the factors of my constant term, divided by the factors of my leading coefficient, which we call q. This will give us a list of all possible rational zeros. So if we have f of x equals x to the 4th minus x cubed plus x squared minus 3x minus 6, what is my constant term? Sorry? -6. And Delina, what are the factors of that -6? So what times what gives me -6? 6 and 1, 3 and 2. Positive, negative. I can have +6, -1, -6, +1, +3, -2, -3, +2. So all those possibilities for the constant term factors, ±1, ±2, ±3, ±6. And Adriana, the leading coefficient, what do we have there? Absolutely. In front of my x to the 4th, what is that coefficient? Well, it's an understood 1. So, Brooke, what we have there as far as factors for 1? It's positive? Absolutely. ±1. +1 times +1, or -1 times -1. So all possible rational zeros are going to be in the form of P over Q. So we put all those factors of P over all of our factors of Q. By this time, since Q is just ±1, listing out all the possible solutions. We come up with 8 different possibilities, ±1, ±2, ±3, and ±6. If we do have a rational zero, it could be irrational, it could be complex, but if we do have a rational or more than one rational, it has to come from one of these. Again, that takes the infinite possibilities down to here, a possibility of just 8. So, here we're going to find all possible rational zeros. In this case, we have f of x equals 3x to the 4th minus 3x cubed plus x squared minus x plus 1. So, Abby, what are my factors for p, my constant term? Tough one, sure, I know. So, ±1 for my constant term. And my factors for my leading coefficient. Well, just 3. What about 1? Factors are 3. So what times what gives me 3? So the only thing is 3 times 1, or a -3 times -1. Absolutely. So -1, -3. And for those rational zeros, again, we put it P over Q. Giving us ±1 divided by ±1 divided by, or ±3. So what do we do from here? We get this as our final answer. What do we do? One, we just have, so we just separate them. So we have 1 over 1 is just 1, and so here we only have 4 choices to choose from. If we do have a rational zero, it's going to be a +1 or a +1/3. Or a -1 or a -1/3. Those are the only choices for our rational zeros. How about this one? We have 6x to the 4th minus x squared plus 9. Again, I'm ultimately going to end up with, we don't have to write this first part here like this, but we know we're going to wind up with P over Q, right? Our constant term factors divided by our leading coefficient. So, what are the factors of my constant term total?
Sorry, on the next slide, number 9.
Factors. So who can help? Factors 9? What else?
You said the 3 twice.
What are factors, folks? Factors are just the 2 numbers that I multiply to get 9. So 3 times 3, we only have to list 3 once, 1 times 9, and again, all positive and negative. And then factors of my leading coefficient. Huh? Absolutely. So 6 can be written as 6 times 1 or 3 times 2. Again, positive, negative, for all that stuff. And then we only have a couple answers, right? Give or take a few more. So we do have a lot of answers here, or not a lot. We actually only wind up, I think, with 16.
Oh.
8 plus or minus. So the best way to do this to make sure that you don't skip any is just take everything in P and one by one take it over one of the Q's. So in other words, first starting off with everything over plus or minus 1 gives us what? So we've taken care of that. Moving on to everything over 2. All right. I already got tired already, folks, or somebody else.
1/3.
Plus or minus 1/3, which we already have. We already have the 3 over 3 gives us that 1, which we already have, so we skip that one. What else?
Plus or minus 1/6.
Well, plus or minus 9 over 3, which is just 3, which we already have, so we've covered everything over the 3.
1/6.
Plus or minus 1/6. Anything else? Because when we do the 3 over 6, that gives us the 1/2, which we already have. 9 over 6, which is 3/2, which we already have. So these are all the possible rational zeros. If I'm asked to find possible rational zeros, that's what we're looking for. There's 16 possibilities here, but isn't 16 better than an infinite amount? It gives us somewhere to start, right? From there, using other tools, it helps us out. I mean, like the other ones, if we found out with Descartes' rule of signs that there are 0 negative real zeros. I know I can get rid of all the negatives, and I should only be looking at the positives, right? So by combining these rules, theorems, we can actually fine-tune it. Find the maximum number of zeros, the number of possible positive and negative zeros, and the possible rational zeros of the function. So, what degree polynomial do I have here, Miriam? 5th degree polynomial. So what is the maximum number of zeros I can have? Have you got it? Maximum number of total zeros.
Oh.
5. Jumping ahead of me. So as far as, 5 total.
Was the 5 something?
Absolutely. So the positive how many positive real zeros? Why only 2? So either 2. Absolutely. There's 2 positive, or 2 changes from here to here. These are the only 2 sign changes. Like I said, 2 or 0. And then what do we do for the negative? Not necessarily multiply, but we evaluate. Right? We stick in negative x for x. Which tells me that f of negative x equals yes. How many sign changes? So here I know for a fact there is no choosing. Like in the previous case, 2 or 0, here I know for a fact we only have 1 and only 1 negative real zero. Right? What are my zeros? What are my possible rational zeros? How do I find that? I take the factors of my constant term divided by factors of the leading coefficient. So factors of 12. Just a few, right? Divided by? So dividing everything by that plus or minus 1. Took care of the 1. How many extras do I pick by dividing it by the 2? So the 1/2. 2 over 2 is just 1. And then 4 over 2 is 2, which you already have. 6 over 2 is 3. 12 over 2 is 6. We already have all that stuff. So, once again, we come up with 16 different possibilities. This last thing here we have that the total number of negative real zeros was what? 1. So does that mean that it's going to come from one of these that are circled? Yes, no? What are these called again?
Possible real roots.
A little bit louder? These are my rational, possible rational, right? What are these? Real. Does a real number have to be rational? Or it could be irrational. So, just because I know that there is one negative real zero, it doesn't mean it has to come from here, because these guys are just rational numbers, right? It is a good place to start, and I'm not going to try to trick you guys up saying, okay, you found one and not put it in there or something like that. But these are things that you have to make sure you don't get confused, real numbers versus rational. All right. Total possible number of zeros here. Total. 4. Again, all coming from, since it's a 4th degree polynomial. For my positive real numbers, or real zeros? 2 or 0. Again, there's only 2 sign changes here, right? I started off positive, positive. There's my 1 negative change. Negative to positive, 2 changes. And for my negative real, exactly, 2 or 0 again. First, you have to make sure you rewrite your f of x as f of negative x. And again, the sign's going to change if it's an odd exponent. It's going to remain the same if it's even. In this case, we can see 2 sign changes, as you guys told me. I'm either going to have 2 or 0 negative real numbers. And then for possible rational zeros, it takes the form of what? P over Q are factors of the 20, our constant term, over the factors of 6. Oh, yeah, there's no 3. Thank you. Over what? And folks, if you stop here, no, that's not the answer. Don't expect me to give you credit, full credit. That was the tough part, right?
1/2. 5/2.
1/2 and, I'm sorry,
5/2.
5/2. And absolutely, it's a 2/2 we have, 4/2 we have, 10/2, 20/2, all the integers that we already have.
1/3.
Is that it, folks?
I want to
I'm just asking if that's it.
Yeah.
I know I usually have you ask a leading question. In this case, I'm asking you. Okay.